Continuing our programming interview patterns, we now look at the binary search tree. You need to have it as a pattern in your head. What is the binary search tree? How do you insert nodes? How do you delete? Code snippets, which are used to delete and insert nodes. Let's begin with what is a binary search tree simply. So, on the left side, all the nodes, as you see, are smaller than the root node. 4, 2, 5, 1, 3 are all smaller. And on the right side, all the nodes are bigger than 6, 8, 9, 7. And this is true recursively, because recursively, if you look at this subtree, then according to the node 4, 5 is bigger because it's on the right side, 2, 3, and 1 are smaller. So this is simply the binary search tree. Let's move on. You can display all the nodes in order. Okay? There is an in order traversal of the tree where you can simply display all the nodes in order 1, 2, 3, 4, 5, 6, 7, 8, 9. You see it's sorted. You can get all the values sorted. If you use a linked list, then in order to find the node, you need to search the whole list. But in a binary search tree, you just start from the root. And if the root is less than the target value you're looking for, this means that your value is bigger. So you are moving onto the right side. Let's see the implementation. So this implementation is trying to find a node. This is the root node, and you need to find this key. So what it's doing is first checking if the root is null, because if it is null, then you just return null. There is no tree. You cannot search for anything. Okay? However, if the root is exactly the key that you are looking for, then just return the root because you have found the key. If you remember, we are trying to find the key on a tree which starts with the root node. If the root key is bigger than the key, this means that our key is smaller. So you need to find our key on the left side. So you simply call recursively. You take the left subtree and you ask the left subtree. Just imagine that you push the job to another worker and you tell it, worker, go to the left subtree because I know that maybe the value will be in the left subtree because it's smaller than the root key, and find me the value. Else this means that our key is bigger than the root. Okay, so we move on to the right subtree and call it recursively. That's it. Now let's move on to the insert method. We assume that duplicate is not allowed and we insert a key into a binary search tree. So here we simply call the insert from the root tree, and we are inserting this key. Okay, so the signature is that it's returning a node, and we insert. What do we insert? We insert a key into the root node starting from the root node. Again, as always, if the root is null, simply return the key itself inside a node, because this would be the new root. If there is no tree, our new key is the new tree actually. Note the pattern here. We are checking for a few simple cases, and when we finish with the simple obvious cases, we move on to the recursion. Now, remember we're trying to insert a key. If the root key is equal to the key, then we throw a duplicate exception because we said we do not allow for duplicate keys. If the key is smaller than the root, then our key is small, so its place is on the left side of the tree. So we call recursively and insert the key into the left side of the tree, and we return the result, which will point to the new root. However, if the key is bigger than the root key, then we move on and recursively add the node to the right subtree. That's it. So let's say we are inserting the value 5 into this tree. We start from the root. Is 5 big or less than 6? It's smaller, so we move on to the right subtree. Is 5 big or smaller than 4? It's bigger, so we move on to the right side. And as there was no node here, we just insert it as a child and return recursively, so we return the original root. Let's delete an item from the subtree. When we delete an item, we need to see if the case is simple or not, because if the node that we are trying to delete has no children, just delete it. If it has one child, replace it with the child and delete it, because then it will not have any children because you replaced it with a child. Another programming pattern here is that you can replace the values. You don't have to replace the pointers. This is a very strong case. In many cases in programming interviews, you can simply manipulate the values. I'm not saying you will do it in real life, but in interview, this will save you a huge amount of times. This is a great tip. The hardest case is when the node has 2 children. What do you do in this case? Let's see. So let's say you want to delete 6. 6 has 2 children, right? So what we do is we move on and find, our motivation is to find a node that can replace 6. So can 8 replace 6? No, because if we put 8 here, then 7 is smaller and it would be on the right tree, and all the nodes on the right tree should be bigger than the node new value we put. So if you notice, then you can always search either for the smallest item on the right subtree or the biggest items on the left. We are going for the smallest item on the left. We find it, it's 7. We move its value to the top. Remember, you can simply exchange values and get rid of this node, just move it to the top. So we search for the smallest value on the right subtree and moved it to the top and deleted the node that was here originally. Let's look at the code for delete. The sample code for delete is as below. Delete this key, some key. So let's look at the signature. Signature is great. We return a node, which is the root of the new tree. We delete from the tree N, we delete the key. If the tree, we start with the cases, you remember the pattern, we start with the simple cases. If the tree is null, there is no tree, there is nothing to delete. We just return null. If the key is the root node, the current root node, remember we're going to do this recursively, so It's true that here we're referencing the root key, but when we move on, the root node would be inside the recursion, so the root node might be even the lowest node. So we check if it's equal to the current key that we are trying to remove, and if yes, then we are starting to check the three cases. If both left and right are null, which means our current nodes which we have found have no children, just return null because we have eliminated this subtree. If the left node is null and we are not on the above case, so the right node is not null, so we are just returning the right node. And why do we return the right node? Because if you look above, then you see that actually our delete helper function is returning a value, and this is the new node. So on the subtree, when we called it, when we returned the right node, this is like a trick. Then the right node would be the new root of the subtree from which we are deleting. So we are mutating the subtree and returning it. Same for the left. And now for the case that we have two children for the node that we want to remove. So we find the smallest node on the right subtree. We didn't actually implement it, but we need to find the smallest node on the right subtree. Okay, remember, you need to implement this. And then you have the smallest node. You replace the smallest node with the root. Our current root is n. You take the smallest one and you put its data and key on the root. You move the data and key into the root. Remember, we said we are exchanging the smallest node from the right subtree into the root. And then we move on to delete this smallest child of the right subtree. And all the above was for the case where we have found the key. But inside this recursion, if we didn't find the key, then we simply move on either recursively to delete it from the left side of the tree if the key we are looking for is smaller than the current root, or we are moving to delete it from the right subtree, that is, if the key is bigger than the current root. I'll put some links to the resources I used here, to an app you can download from the Play Store, and some resources to books. I'm going to put the resources with the affiliate link. Please use it. It will help me. I will get something out of these videos. For the books, there will be an affiliate link to buy the books, but I'm really recommending the best books that I am personally enjoying reading. And it's not the most used book, not the most common ones. And I'll put a link also into the Play Store where I used an app to see all this data. Thank you for listening, and I will see you next time.